last session we have completed with constant pressure process and its numericals. In today's session we are going to study constant temperature process, that is isothermal process, and we'll also see numerical based on this topic. This is Faizan Kagdi and I welcome you all to our lecture series of basic mechanical engineering. So let's begin. Now if you remember that we have discussed during Boyle's law how we can achieve constant temperature. We have taken a case of work done on the system in case of a closed piston cylinder arrangement. So again we can take an example that when a force is applied on a piston for compressing the gas, it is required to push a piston at a much slower rate so that system gets a time, or we would say gas gets a time to reject its heat energy to the surrounding atmosphere, which means infinitely slowly we need to push a piston in a downward direction for compressing the gas. Then and then only at final state we can achieve constant temperature. Similarly, when we require to obtain work from the system, that is work done by the system, this can be done by supplying heat energy to a gas. So again the same concept is applied. So when a heat is supplied to a gas, then obviously there are chances that the temperature is going to increase along with the increment in a pressure, and piston will move in upward direction. But to achieve a constant temperature at final state, it is required that the piston has to move at a much slower rate so that a gas gets a time to reject heat energy or whatever increment in the heat energy takes place to the surrounding atmosphere, so that at a final state when a piston has achieved with a higher volume, its temperature is maintained constant. So whenever we represent this process on a PV diagram, the curve is a hyperbolic curve, as you can see on your screen. So we have taken an example of a work done by the system. So at initial state, during expansion process, pressure will be higher and volume will be lower, and when it pushes the piston in upward direction, so pressure will be reduced and volume is going to increase. As we know, P is inversely proportional to V. Okay, so according to that, now we should be clear that we need to do 5 tasks which we have done in our previous process, that is constant pressure process, and even in constant volume process. That is, we need to determine how much work is done during this process, that is isothermal process. Then how much is a change in internal energy. Now will there be any change in enthalpy, that is delta H. How much is a heat transfer during this process. And last, that is relationship between pressure, volume and temperature for our isothermal process. So let's begin first by determining how much work can be achieved during this process. So we know the general formula of work output, that is work done is equal to pressure into change in volume. Now the equation will be integration from state 1 to state 2 P dV. Now if you notice carefully, so in this equation both pressure and volume will be variable, right? Our target is to maintain constant temperature. So we know that pressure is also going to change and volume is also going to change. But in order to find out total work done, we need to integrate this equation with respect to volume, right? So pressure is a variable, so we cannot use that. So we need to convert pressure in terms of volume, or we need to form equation in which pressure can be expressed in terms of volume. So we know our equation from Boyle's law, that is PV is equal to constant, that is C. So by using that we can write P is equal to C by V. So in this next step you can see I have written work done is equal to integration from state 1 to state 2 C by V dV. Now C is constant, so taking C out and we can say integration V1 to V2 1 by V dV is what? So we know it is ln V. So we can say log V to the base E. So I have written and applied the limits, that is from initial volume to final volume V1 to V2. Now after substituting this value, we can say the answer next step will be C log V2 minus log V1. Now in this case we are going to apply our log rule. So log V2 minus log V1 will become, we would say in a ratio, that is log V2 by V1. So I have written directly, that is W is equal to C log V2 by V1 to the base E. Now in this step we need to substitute the value of our constant C. So we know that applying constant C at state 1 and state 2, it is going to become P1 V1 is equal to P2 V2 is equal to C. Right. So substituting the value W is equal to P1 V1 log V2 by V1 to the base E, and even we can write from characteristic gas equation, that is P1 V1 is equal to mR T1. So further I have written the equation W is equal to mR T1 log V2 by V1. Now even we can write V2 by V1 in terms of pressure. How? So we know our equation P1 V1 is equal to P2 V2. From this equation we can say that V2 by V1 is equal to P1 by P2. So our final equation can be written as mRT1 log P1 by P2 to the base E. So this is an expression to determine work done. You can use either of the formulas depending on the data available in numericals. If volume is available, then we can use our first formula in terms of volume. If pressure is available, then we can use our second formula, which is in terms of pressure, to determine work output. Now next we need to see change in internal energy. So as we know, the formula that is of change in internal energy delta U is equal to mCV T2 minus T1. That is, this is our maximum change in internal energy which can be achieved. But we know that internal energy is a parameter which depends on temperature. That is basically on change in temperature. So we know that in our case there will be no change in temperature when the system moves from initial state to final state. So we can directly say that there will not be any change in internal energy, that is delta U is equal to 0. Right. Now let's see our next parameter that we need to determine, that is heat transferred. So as we know that according to our first law of thermodynamics, that is Q is equal to delta U plus W. But in this equation it is very clear, we have determined a work done during this constant temperature process and even delta U. So delta U will be 0, indicating that Q is equal to W, which means that whatever heat is supplied during this process is completely converted into work transfer, which in actual case is not possible. So it is basically hypothetical condition to achieve constant temperature, which indicates a 100% conversion of heat energy into work output, that is Q is equal to W, which in actual case it is not possible. 100% efficiency is not possible. Even we know that heat is a low grade energy, right? But according to this process we need to determine heat transfer. So we can say that the equation of heat transfer will be equal to the equation of our work done. So Q is equal to, we can directly write P1 V1 log V2 by V1. So this is our third task which we have determined. Okay, now next task is to determine change in enthalpy. So as you can see on your screen, delta H is equal to final enthalpy minus initial H2 minus H1. After substituting all the parameters, we know that delta H formula comes equals to mCp T2 minus T1. Again, this enthalpy parameter depends on a temperature. That is, change in enthalpy depends on change in temperature. But in our process, as we know that there is no change in temperature, so delta H will be directly 0. So delta U is 0, remember, and delta H is 0. And W is equal to Q. Okay, so I hope that you are clear up till here. Now let's see our last task, that we need to determine relationship between pressure, volume and temperature. So as we know, our combined gas equation, that is P1 V1 by T1 is equal to P2 V2 by T2. This equation we have achieved by applying it on state 1 and state 2. Now from this equation it is very clear that for our particular process of constant temperature, T1 will be equal to T2. So the final equation is going to become P1 V1 is equal to P2 V2. Okay, so we have completed our 5 tasks. Now I hope that you are clear with this process, constant temperature process. Now let's see numerical based on this process. So now as you can see on your screen, a question is displayed. 1 kg of gas at a pressure of 100 kilopascal and temperature of 17 degrees Celsius is compressed isothermally in a piston cylinder arrangement to a final pressure of 2500 kilopascal. So in a question it is given that a gas has a mass of 1 kg, that is m is equal to 1 kg. Initial pressure, that is P1, is given 100 kilopascal, and temperature is given 17 degrees Celsius, is compressed isothermally, which means initial temperature is equal to final temperature. So T1 is equal to T2 is equal to 17 degrees Celsius, and the final pressure achieved is 2500 kilopascal, that is P2 is given 2500 kilopascal. Now in the next statement it is given the characteristic gas equation is given by the relation PV is equal to 260 T, where T is in Kelvin. So we need to determine first final volume is how much, compression ratio, then change in enthalpy, and last work done on a gas during compression process. So now over here characteristic gas equation is given. So usually we take PV is equal to mRT. So we can compare that equation with the given equation, that is PV is equal to 260 T. So in this mR is equal to 260, we can say, that is in place of mR over here it is given 260. Now since mass is 1 kg, so we can say that characteristic gas constant R is equal to 260, right? The most important thing which we need to keep in mind is that over here the value of R, that is 260, is in joule per kg Kelvin. In usual case, if you have noticed that taking a case of air, so the value of R for air is 0.287 kilojoule per kg Kelvin. So when we consider it in joule per kg Kelvin, then a value of R will be 287, right? So it is very obvious that over here it is given 260, which means the unit of R will be in joule per kg Kelvin. This is an important thing which we need to keep in mind. Now let's begin by writing a data. So as you can see, I have written a data. M is equal to 1 kg, pressure P1 is 100 kilopascal, P2 is 2500 kilopascal, T1 equals to T2, converting it in Kelvin, that is 17 plus 273, which means 290 Kelvin, and PV is equal to 260 T. Now we need to determine V1 is how much, compression ratio, that is small r, is how much, delta H, change in enthalpy, and work done. So first let's determine a final volume, that is V2. So for determining it, we are going to use our characteristic gas equation, which is given PV equals to 260 T. Now the equation with respect to final volume will become P2V2 is equal to 260 T. Now we know the value of P2, which is 2500 kilopascal, but since R is 260 joule per kg Kelvin, we need to take pressure in Pascal. So for that I have written 2500 into 10 raised to 3, remember, into 10 raised to 3, that is kilo, into V2 is equal to 260 into 290, that is temperature. So finally it is very simple, we can determine V2 is equal to 0.03016 meter cube. So our first task has been completed. Next, compression ratio. So compression ratio will always be equal to initial volume, that is V1 by V2. For example, expansion ratio we are going to consider, that is V2 by V1, that is final volume upon initial volume. So similarly compression ratio will be initial volume upon final volume, that is V1 by V2. So for this equation it is required to determine a volume, initial volume V1. So for this our first task will be to find out V1. So again using our characteristic gas equation, P1 V1 is equal to 260 T. So substituting our values, 100 into 10 raised to 3 into V1 is equal to 260 into 290. So V1 is equal to 0.754 meter cube, and finally the value of R is equal to 0.754 upon 0.03016. So R is 25. That is the compression ratio. Okay, now next task, to determine change in enthalpy. So it is very obvious that since temperature is constant, so change in enthalpy will be 0. So as you can see on your screen, delta H is equal to mCp2 minus T1 is equal to 0. Now next, we need to determine work done on gas. So as you can see on your screen, I have written a formula of work done which we have derived in our previous topic, that is work done is equal to P1 V1 ln or log V2 by V1 to the base E. Now see carefully whether the requirement of a formula is satisfied or not. So we can say that P in place of P1 V1 we can write mRT, that is in our data it is given 260 T, where T is a temperature which is known, that is 290 Kelvin, and even we have determined V1 and V2, right? So can I say that we can directly place a value of compression ratio R? That is, we know that R is equal to V1 by V2, and over here log V2 by V1. So V2 by V1 is a inverse of our compression ratio, that is called even it's called an expansion ratio, right? So over there I have written 1 by 25 in log. So we can write final equation, that is 260 into 290, that is temperature log 1 upon 25 to the base E. So final answer of work done is equal to minus 242.70 kilojoule. So over here you have to mention that a negative sign in work done indicates that work is done on the system for compressing the gas. Okay, so these are our final answers. So I hope guys that you are clear with the concept of constant temperature process along with this numerical. So today we are keeping up till here, and we'll continue with our next process, that is adiabatic process, in our next session. Till then, stay tuned and thank you all.